Okay, this is gonna feel like cheating. It's not cheating. This is right from your textbook, page 297, example 4. Can you write a function, call it f of x, its derivative has to be tangent x, and it has to be true that when you plug in 3 for x, you get 5 as the answer. So, it's not cheating. I promise it's not cheating. This is what we're going to do. We're going to write f of x. We're going to use an integral to write this function because we know that if we write the integral in the correct way, we can take the derivative of that integral and get out any function that we want. So we're going to start piecing together this function. We know, because we just did an example up here, that if we wrote a function whose upper limit, that's based on an integral, whose upper limit is x, and has tangent t dt as the integrand, then when we take the derivative of it, as long as the bottom is a constant, we're going to get out that tangent function with a variable change. We're going to get tangent out at the end. So everything we have right here, as long as we make that lower limit a constant, then the derivative will work out right. So the question is, how do we pick the constant right so that we can make this true? F of 3 will be 5. We're going to use a little bit of what we practiced up here. If I make that lower limit 3, then I want you to imagine what f of 3 would be. F of 3, I would plug in 3 for x, and I'd be taking the integral from 3 to 3 of tangent t. Well, that integral is going to have a value of 0. If I have a 5 out here, you could add it at the beginning, you could add it at the end. Now think about this function. When I take the derivative of f, the derivative of 5 is 0, so that's not going to contribute. The derivative with respect to x of this integral is going to be tangent x, so that means I've met the criteria that the derivative is tangent x. And imagine plugging in 3 for x. That means the whole integral is going to be equal to 0, and the only thing left is going to be 5. So I've written a function whose derivative is tangent x, and for which f of 3 is 5. Okay, so try this one. I have a tree trunk, and I know the rate at which the radius of the tree trunk is changing. So tree trunk, right, over the years, probably it's getting wider and wider. So I know that when time is 0, the radius is 6. Oops, I need a pen. When time is 0, the radius is 6. And capital R is the radius function. So that tells me that R of 0 equals 6. I need to write an expression involving an integral for the radius of the tree trunk. Here, when they're saying for 0 to 3 years, that's just to saying, because we only know that the derivative function is good for 0 to 3. So they're saying, well, I'm not trying to trick you by going outside that domain. And then in a second, I'm going to use that expression to find R of 3. So I'm going to write a function R of t, the radius of the tree trunk as a function of time t. This is just, it's very similar to the example we just did. I'm supposed to write a function, and I know its derivative should be this. And I know one ordered pair on the function should be this. So I'm going to make an integral. The upper limit should match this variable. If I want t to be the variable of my function, then t has to be the upper limit. Cool. That lower limit's going to have to be an integer. A constant. Here, I'm going to write, essentially I need dr dt. The problem is I can't use t because t is the variable in my integrand here. So you could just name another variable. Pick your favorite variable. I'll go back to blue. dr d. You could use x. You could use w. You could use any letter you want. Times dx. You could also have written out this function, so 1/16, 3 plus sine of x squared. So any version of that function, but we can't use t as the variable because t is going to be the upper limit. So what should I make the lower limit of my integral? Well, I know this times 0. So I have to think of the input value for the ordered pair I know. That's going to be my lower limit. And then this 6 is going to be the number I add in front. And then you could double check. If you found the derivative of r with respect to t, you would be taking the derivative of this expression. The derivative of 6 is 0, so it doesn't matter. The derivative of this integral, well, the dx's cancel, and I'm finding dr. So it would be whatever dr dt is, but with a t plugged back in. And you could imagine plugging in 0 for t. The value of that integral becomes 0, and the final answer, r of 0, would be 6. So, hold on one second. The other thing I was asked to do is find r of 3. So just notice you would find r of 3 by plugging r in for t. Does not get plugged into the function that's in your integrand. It's going to be 6 plus the integral from 0 to 3 of, on your calculator, what you would type, 3 plus, oops, 1/16, 3 plus sine of x squared dx. I don't happen to have my calculator with me, but that's the math you would do to find the final answer for r of 3. If you just wrote this expression on your AP test, you would get 1 point and then the second point for actually plugging that into your calculator and evaluating the answer. Okay, last one. Again, this is why that was the most important example in all of Chapter 5, because we're going to have a lot of situations where we've been given a derivative function, and we're going to have to write the parent function, the antiderivative function. So a particle moves along the x-axis so that its velocity is sine of t squared. And we know that that function is good on the domain 0 to radical 5 pi. We also know that at time 0, the particle is at position 5. That's what x of 0 equals 5 means. It says find the position of the particle at t equals 3. Well, that's essentially asking me to find x of 3. And I hope you will continue to strive to not try to tell me what x of 3 is until you can give me a whole function, x of t. So that's our job here, is to write essentially the position function given the velocity function. We know velocity is the integral, the area under the velocity. Position is the area under the velocity curve. But again, this is like that most important example that we did a second ago. So the x function is going to be, well, it's supposed to have a derivative that is sine of t squared. Here, pick some other variable. I don't know, p? Anything you want. The limits are going to be, well, the lower limit is going to be the input value for the one ordered pair I know. The upper limit is supposed to be whatever this input variable is, so t. And then, do I need a number out here to add or subtract so that when I plug in 0 for t, I get 5 as the answer. So we get 5 as the answer here. So that was your first step, is to write an expression for x of t, the position function, and then we're asked to find x of 3. I want to be very, very clear here. I'm plugging in 3 for t, and this function only has one t in it, and it's that upper limit of the integral. So this has to be the integral from 0 to 3. Sine of p squared, that's not a t, so don't go plugging in a 3 for a p. 3 is, you're only going to plug it in for t's. So this is still sine of p squared dp. Now obviously your calculator only has the variable x, so when you type this in, you're going to be typing in 5 plus the integral from 0 to 3 sine of x squared dx.